Hi, kids. Okay. All right, we're going to do this problem. You guys should have. It's a Faraday's Law problem. A 20 centimeter by a 40 centimeter coil with 5 loops has a resistance of 4 ohms. It is directed the same way as an 8, a little MT, that stands for 8 millatesla magnetic field. If the coil is rotated so that 0.2 seconds later, it is directed perpendicular to the magnetic field. What is the current induced in the coil? Wow, that's a lot of words for one problem. But essentially, I'm asking you guys to find the current. If you guys think back to our last unit, I'm asking you to find the current. You know the resistance, so we need to find the voltage. Well, how are we going to find the voltage? Well, we're going to use Faraday's Law, which is what this is all about. So this is Faraday's Law, which you guys should already know. But just a real brief reminder. Negative, don't worry about the negative for right now. We'll talk about that more when we get to Lenz's Law. N is the number of turns or number of coils in our loop, which in this problem we have 5. This is the change in flux, and this is the time that this change in flux occurs. This symbol stands for electromotive force. It is essentially just voltage. So you might ask, well, why the heck not just call it a V? Because since it's the same thing as voltage. And the answer to that is this V comes from a separation of charge. Like in a battery, you get the voltage because there's a separation of charge. Where this voltage, and it is voltage, okay, comes from a changing flux. So physicists say V to remind themselves, hey, this comes from a separation of charge. And they use this script E to remind themselves, oh, this voltage comes from a changing magnetic flux. Okay? All right, so there's our little intro. But I would recommend, as always, to try to sketch a picture of what's going on first. So if here is my area, now I realize the area is not actually a loop, it's a rectangle, but you get the idea. The direction of the area always points perpendicular to its surface. So it's going to point like that. So if here's my area, its direction points straight up or straight down. If I rotate it, you can see how it rotates around. And then at the beginning, it says my magnetic field's pointing the same way. So my magnetic field's going like this. And you can see that there are magnetic field lines going through the loop, so it definitely has a flux. Later on, 0.2 seconds later, it says that you rotate the loop so that now the magnetic field and area are perpendicular to one another, so there would be no flux. So this would be going, okay, I'm rotating like this, so it goes from lots of flux to no flux. Okay? All right, so let's do our problem. I'm going to be using my equation here. I know that N is 5, and then I need to find my change in flux. Okay, anytime you do change in flux, that's going to be your, anytime you do change in anything, it's final minus initial. Okay, well, my final is 0, because that was my picture. So my change in flux is going to be 0 minus, remember the equation for flux is Bakos, BA cosine theta. Okay, so if I want to find my change in flux, it's going to be B, which in the problem was 8 millateslas, which is 8 times 10 to the minus 3 teslas, times my area. My area was 20 centimeters by 40 centimeters, and yes, you do have to remember, basic area formulas. So if I want to do this in meters, I'm going to do 0.2 meters times 0.4 meters, and then that's my problem, and then I go cosine of 0 degrees. So if I plug my stuff in, my change in flux is going to be, actually that is a negative sign, so my change in flux would be, get your calculator out, do it with me, HE negative 3 times 0.2 times 0.4 equals 0.00064 Webers, or if you want Tesla meters squared, same difference. All right, I'm back. All right, so we have our change in flux to be 0.00064 Webers or Tesla meter square. All right, so then we got to plug it in. So if we plug this back into our equation, we are going to get -5. The change in flux, remember that was minus, sorry. Minus 0.00064 divided by the time, which was 0.2 seconds. So my EMF, or voltage, is going to be times 5 divided by 0.2 is going to be So that's how much voltage is induced across my loop. And then I'm not quite done yet because I have to find the current. So I'm going to then use my Bernoulli's equation, plug it in, and solve for my I, and I get my current to be 0.004 amps. Okay, so yeah. So not too bad. Just remember you gotta set stuff up. All right, bye kids.